So it is time to start the seminar. So today I have the pleasure to have one of my friends here and closest colleagues in the aerospace department. So Professor Dimitra Panagou. So yeah, Mika, she comes from Greece, where I am from, same university. So this is very nice, you know, I mean, to reconnect here. It's a pleasure. So she did afterwards her postdoc at the UIUC. She had also stint at Penn. Again, I was at Penn. So again, very nice to reconnect. So many things that you're
entanglement of Greeks going around.
It is someone to admire, at least myself as a young faculty. It has so many young investigator awards like NASA, Air Force, Career, maybe a DARPA will come. So yeah, I will give you the podium. And
thank you so much, Vasily.
Yeah, I look forward to the talk.
Okay, thank you very much for being here. This is a very dry run of a plenary talk that I'm planning to give at CDC in December. So please save all your very good feedback at the end. I'll try to do 50 minutes. It's not going to be probably more than 50 minutes, but all your very, harsh feedback, I'm looking forward to receiving it. So the talk is about our work on safe and resilient autonomy using synergistic control, estimation, and learning. And I'm going to give you the outline of the presentation. I want to talk about an autonomy architecture that we have been developing over the years and go through, in more technical detail, through some components and their interconnections in that architecture that involve estimation, control, planning, and exploration techniques. Time permitting, I would like to spend a little bit of more time to describe some of our group's work on control barrier functions, and I will finish with some conclusions. So our work is aiming to enable autonomy for robotic and cyber-physical systems. And what that means is that we would like autonomous agents like robots to be able to operate independently in their environment and be able to make autonomous decisions and act and interact with their environment without the supervision or intervention of humans. And we would like particularly to do that in challenging environments, in environments that are uncertain, that they are unknown, like when we use robots to explore the other planets, to environments that are dynamic and dangerous and in areas that we would not like humans to go very close, or in environments that are going to be congested in urban and suburban areas. So in order to enable this vision, I would like to argue that this architecture, this autonomy architecture, is in fact a feedback loop. It's a very big feedback loop. And why am I saying that? So consider that you have your robot, typically the plant that we are thinking in controls, and this robot is operating in an environment. And this environment is in principle cyber-physical in the sense that it has physical entities, physical obstacles, other robots, humans that your robot needs to avoid and interact with. And it's cyber because it also includes the information that the robot has about the environment, that it becomes available to it either through communication with other robots or through sensing typically on board the robot with its sensors. So what you also have on your robot is a control module, an actuation and control module with which your robot is going to move in the physical space. And what you want is, given some reference, you would like your robot to use information, feedback about its environment through sensors and possibly communication, and design a controller, make a decision on how to move this in this environment. So essentially here, I'm just closing the feedback loop that we usually also show in our undergraduate controls classes. So if you want to see in a little bit more detail than what this reference to the robot is going to be, then you will probably consider that there are specifications, requirements, constraints that describe the mission for your robot. And you would like, and these specifications might affect directly your control design, constraints, for example, but also dictate typically the task. Different level in your architecture is the tasking what is the task that you would like your robot to execute? For example, it could be avoid the obstacles, go to a goal location, visit the goal location that often, and so on. So the mission specification in a more abstract level, which typically needs to be interpreted into a path that the robot will need to follow through the planning module. And typically that path will become a reference through waypoints, for example, to the controller in order to further close that loop. So this is for a single robot, and typically that would be an architecture for a relatively static environment. But we talked about environments that are going to be in principle dynamic and uncertain. So adaptation comes into the picture, and you will want to have some form of adapting your model or your control structure that would also possibly include the adaptation of the planner. How you generate the path could be adapted, might need to be adapted. What the task is going to be, if needed, to change throughout your mission, or the specifications that you might want to, that nominally you have for your system. All this can be part of an architecture for a single robot, and you can only imagine that this architecture becomes even larger scale if you have a multi-robot system. Okay, so what I am arguing is that for the most part, these problems are very complicated problems, and they have been addressed in the literature typically by taking a decoupled viewpoint. From the perspective of, we typically focus either on how to just design the controller or just the planner, or how to just do like the very high level tasking and so on, without maybe paying that much attention in the interconnections between them. And that is, there is a good reasons why people are doing that, because definitely that simplifies the overall design. But at the same time, that can come at the cost of producing solutions for each one of the components of the layers of the architecture that are going to be inconsistent across layers. On top of that, there are also other considerations and real challenges when it comes to how to design such an architecture from the perspective of typically different parts of the problem might require models of different fidelity. Or they might describe phenomena that they evolve along different spatiotemporal scales. And of course, constraints and uncertainty typically scan through the entire architecture. So how can you solve these problems? And is what I would like to discuss today, or at least how you can solve some of these problems, and particularly by focusing in some of those interconnections on top of the design of the individual modules. So that brings me to a more technical part of my talk. I would like to start with observer-controller interconnections, focusing maybe in a more classical loop that we want to close, how we can close the loop between observers and controllers when you have safety constraints that need to be addressed. And quite some of the rest of the talk also is going to be based on control barrier functions. So let me introduce them in order to make sure that we are all on the same page. So I'm going to talk about robots that, or in general, agents, autonomous systems that are described by nonlinear control-affine dynamics. And I'm going to consider that their operation is subject to safety constraints that define parts of the state space that are your safe set, which is typically the super-level set of a constraint function H. And our objective is to design the controller for this system so that the closed-loop system trajectories are safe, meaning that if you start from within the safe set, you're always going to remain, like the trajectories of the robot will always remain within the safe set. So this problem is it's not a new problem, and in fact, it has been studied with various methodologies. One of them that has been developed in recent years is the concept of control barrier functions, which says that if this function H is such that you can find the class K function so that this condition here holds, which I should probably define it. That's the time derivative of the constraint function along the trajectories of the system. And if it is bounded by this lower bound here, essentially, if you impose a rate of change on how your constraint will change along the direction of your closed loop dynamics, then this is called a control barrier function for the system. And it can guarantee that if then you apply a controller that you can compute out of a quadratic program of this form, then the closed loop trajectories will remain in the safe set. So you can think of it as a constraint that imposes safety in the sense that it always tries to enforce safety constraint so that your controller view does not stays as close as possible to a desired control input, but does not violate safety if these two are incompatible. But of course, that would be a nominal system. Typically, we have disturbances that are acting on our dynamics. And in that case, you can use robustification arguments in order to describe a robust version of a control barrier function. So the difference here in the condition in the control barrier function definition comes into the picture because you have now the disturbances also acting in the dynamics. And the idea is very similar. You can, if you can find a function such that this condition holds, then this is called the control barrier, a robust control barrier function for your system under disturbances. And you can design a safe controller in that case by forming such a quadratic program subject to your robust control barrier function condition. Okay, so far, but typically what is happening is that when you want to implement such a closed loop controller, you are not going to have, it's very likely that you're not going to have your entire state vector available, but only an output vector y. And that is going to be given by an output model, typically also subject to some disturbances, for example, sensor noise. So then things become a little bit more complicated, and you have to be careful in how you're going to design your controller. In the sense that now what you have available for control would be at best an estimate of your state that you're going to obtain somehow from some observer. And that exact robust CBF is not going to do the trick because it assumes that the state here is perfectly known for safety. Okay, so if you only have an estimate of the state, you have to be careful. And in fact, you can see in the hard way that if you do a stable control observer, you have designed your Kalman filter, your lubricant observer, depending on your system and so on, to be stable, and you have a CBF that is safe, that you have tuned it to be safe, but their interconnection is not necessarily safe. Why? Because there's an estimation error that you have to also account when you're closing the loop. So we don't want that case to happen. We would like that case to happen so that the quadrotor does not, is able to stop at the physical obstacle and not crash. Okay, so how do you do that? You're essentially, we studied this problem a couple of years ago, and the idea is that you have your, again, just summarize, you have your nonlinear system with an output, output feedback available, and you want to synthesize an observer for your system state and the control input that now depends on your output and the observer, as well as the initial conditions for initial estimates and initial states, such that overall your interconnection is going to be safe. From the perspective of the actual trajectories of the quadrotor will stay within the safe set. And the key is, as we're going to see, is that you want to start sufficiently safe, so sufficiently into the interior of your safe set, with a small enough estimation error that you can bound in order to be able to guarantee safety throughout the trajectories of the system. So in our paper, we studied two approaches, two different observers, essentially, that have the desired properties that we would like to have for this interconnection to work. So I'm going to give some more technical details about the first approach, which assumes that we have an observer that we have taken from the literature that is input to state stable, meaning that the observation error is guaranteed to satisfy the input to state stability condition, which means that essentially we can bound this error with a non-increasing function m, like this. So given the bound, then that's a key information because combining it along with Lipschitz property of your constraint function h, which is the function that describes your control set, you can show that if this condition holds now for the value of your constraint function for the estimates of your system, so if that bound is met, then that implies also that the true state of your system will lie within the safe set. So your constraints are going to be met. So essentially, instead of trying to impose this constraint, you want to design your observer and your controller such that this constraint here is met. And now you can do that by following the usual mechanism of a control barrier function along the dynamics of your H function, along the estimated trajectories. I'll spare you from the technical details, but essentially you can define what we call observer robust control barrier function that takes into account the fact that you have to account for an estimate or estimation error here. And you can write the result in a nice theorem that can help you also specify the set of initial conditions, and the set of control inputs that you want to choose are such that now this condition here is met out of the analysis that you get from the derivative essentially of your H function. Intuitively, what is happening here is that you, compared to your earlier form of robust control barrier functions with perfect state, what you're doing is that you're making your condition more conservative because you have an estimation error that you have to account for. But overall, because you're assuming that you have a stable estimator, this error is going to become smaller because that tends to zero. Because so eventually, the more accurate the estimation, the less conservative you're going to become over time. Okay. So, and in fact, if you write down the specific case where you have linear class K function and exponential observer convergence, then you end up having essentially the robust CBF condition, which intuitively it says us what we know for stability as well, that you want to design your observer to converge faster than your controller for safety. So if that is met, then your design can be even easier. So some simulation results that essentially justify or verify the case studies that I was showing earlier. So if you have a safe controller, but without accounting for the estimation error, then collisions can happen, which is not what happens if you do the approaches that we have in the paper. And to show again the bad case and the good case, crashes happen if you don't take the interconnection safely, but if you apply an observer controller interconnection as I described in the earlier slides, then the robot will be able to essentially start decelerating early enough so that it just goes around the wall. That was its nominal trajectory, but it was able to not get crashed. Okay. So I was talking about perception and sensing here. So I just want to acknowledge that the perception in the loop is more than just doing state estimation. and involves also the problem of navigation from the perspective of localization, building your local map, the local map for the robot to move around the obstacles. This is ongoing work. I'm not going to spend time on explaining, this part of the work in this talk, but I'm happy to talk about it offline if you're interested. So with that, I would like to focus a little bit more into the planning and control interconnections that we can define so that the planners that we are developing can become consistent and safe along with the underlying controllers. And I'll refer to some work that we have done jointly with Aaron Ames and his group. So I've been thinking about this problem that, again, typically you have a planner that is going to decide the path for the robot, the waypoints to follow, and then the controller that is going to design the control actions to track this path and the waypoints. And typically, you are solving your control based on your nonlinear dynamics, often with a continuous time representation. But for your planning, you might need to do, some optimization to optimize some objective functional on how the robot is going to move around. So you want to do that with a simpler model, typically a linear model, and often at a different time scale, and in a representation that needs a discrete time modeling. So these two are going to have some mismatch with each other. And if you just feed your planner, the result of your planner into your controller, it could be that the plan might not even be followable with your nonlinear dynamics. So you need something in between that tries to bridge the two, okay? Or you need to design them carefully in some sense. So what can you do? One idea that we investigated was for the class of systems that are differentially flat, we used the transformation of the nonlinear dynamics into a linear flat space, which is exact. So if your system satisfies this property, then you can have a transformation between linear and nonlinear that is exact. And that means that then you can do your control on that flat space because it's linear, and you can make use of your nice properties of linear systems. And then if you want to have a different time scale via discretization for the planning layer, then you can do that with zero order Hall discretization and typically not lose anything. So very briefly, what you can do essentially is to do your tracking control on the flat space, and you can guarantee that your system trajectories will stay within a tube around your reference. And then this tube, you can have characterizations, exact characterizations of what this D is going to be. And then you can use that D when you are designing a tightened safe set in your flat space that encodes, again, a smaller version of your safe set. So by how much you need to shrink your safe set is given to you from the properties of the tracking layer. And with that, you can have a planner that's going to give you the way of guaranteeing safety for the closed loop trajectories. Why? Because essentially you will force your planner to always plan in the tightened safe set, which is this part. And that gives you the guarantees that the trajectories will never get into the unsafe set, which is this part, okay? And so if you're interested in further technical details, what is nice, and it really makes an interconnection here, is that the way that these two work together does not guarantee only safety, but also guarantees recursive feasibility for the planner, which is an MPC in this case. So I'll save you from the technical details. It's a rather long paper, but if you're interested, that's the title of the paper. And we have also implemented that on our robots. I will skip the video in the interest of time. Okay, so we start seeing ideas on how to bridge the different architectures with different models, but we have used an underlying assumption that there's a differential flatness condition that needs to be met for our systems. And that is a standard, it's a property that holds for most of vehicle type of robots and so on, but it might not work for all systems. So then we kept thinking about this problem, and we were thinking that ideally what you want to do is really have your favorite controller and your favorite planner and have something that is going to make them work together safely in between without you caring that much of the choice on the individual planner and controller. So maybe you need an additional module in between, which we call that gatekeeper. Actually, my student called it like that. I think it's a nice name. Because you want to verify online, essentially, if the nominal plan, the nominal trajectory that your planner is giving you is going to be safe over a finite horizon ahead, so that you can feed it to the controller. And if not, you want to do something that is going to be safe. So what is the principle of the gatekeeper? So the idea is that you are maybe at some initial time, and the knowledge that you have about your environment is that part here of your state space. So maybe that's the known safe set, because that's what you can see that is obstacle-free in front of you from your perception system. And so what you are doing, what Gatekeeper is doing, is that it forward simulates, propagates the nominal trajectory that the planner is giving to it for up to some time t, and then it checks with a backup controller whether this trajectory at the end of a finite horizon will go into a safe set, into a subset of the currently known safe set. If that's the case, then it commits the trajectory and it sends it to the controller. So the controller will move the robot. Then at the next iteration of the algorithm, you're going to be at a different part of the state space that you have more knowledge about your environment. You do the same idea, and you only essentially send the trajectory to the controller to be executed only if you can verify that it can be safe with a backup controller. If you find a time instance that the trajectory is no longer safe, what you do is that you convert back to the previous committed trajectory that was safe, assuming, of course, that nothing has changed in the environment in between, and you execute essentially the behavior of the backup controller. So, okay, that would be like how the architecture looks like. I'm not going to explain the architecture here, just want to show to you that now all the elements that we have for the low-level dynamics, tracker controller, observer controller, are also taken into account here in this architecture in the Gatekeeper. And some simulation results about where that can be useful. So this is a case where you have a vehicle that needs to go and track the fire front with information about the upper bound of the fire spread. So you have a dynamic environment, but you have some knowledge about this environment, how it's going to change. And what you're seeing here is the behavior of the Gatekeeper, which is the green trajectory, relative to a backup filter, which is a more conservative controller that is safe, relative to a MPC. That look what happened to the MPC. The MPC is getting trapped here in this pocket because it thought that it was safe at that time to get into and didn't have enough finite horizon ahead to see that it's not going to be safe in the future. Gatekeeper didn't get trapped because it knew it was not, it couldn't guarantee that it would be safe and there would be a backup action to take it out to safety, so it didn't get trapped. You can also do similar motion planning problems with Gatekeeper if you want to go through fast flight, through forest type of environments. And in fact, it also performs better compared to MPC implementations from the perspective of being much faster at every iteration, and also having to stop fewer times for backup safety compared to MPC in terms of deadlocks that were encountered. And in fact, you can also implement that on board actual robots. So this is an experimental implementation from our lab, where the idea is that the robot needs to go to this goal location, that there is a lot of obstacles here, that it doesn't know the environments, the obstacles in the environment a priori. It builds the safe flight corridor as it flies. Okay, so it can only fly within the part of the safe flight of the flight corridor that it can be certified to be safe. So the Gatekeeper doesn't allow it to go through here because it doesn't know that it is safe to, that it does not know that it is safe to go here. We have a naive exploration algorithm that takes the robot around until it finds a safe path. One exists. We have set the environment so that one safe path exists. And eventually what is going to happen is that the gatekeeper will make the robot go around that is more open here and safer, can verify that safety will be maintained, and will land the quadrotor safely. So I have to make that video shorter. So let me move on and go to the next part of the problem. So, okay, so essentially you can use properties, structure of the system through differential flatness in order to bridge your planner and controller to be consistent and have safety guarantees and recursive feasibility guarantees. For gatekeepers, similarly, under the assumption that you have a backup controller, that's a big assumption, we can discuss about that, then you can still have this type of recursive safety and recursive feasibility guarantees. But as you have seen already, probably you're thinking, okay, in this type of problems, how do I even decide where the robot needs to go? Like, it doesn't even have a map of the environment. So how does the robot explore? Which is the last part of the architecture that I would like to describe here, with tasking being essentially more of an exploration task for us. Okay, so, and in order to make this problem a little bit more abstract, let me remove the obstacle environment assumption at this point, and let's consider that you have a robot, that it has a limited sensing area, and it wants to go and collect, essentially explore the environment in order to learn something about this environment. So it has a sensing area that is limited in the sense that, maybe it's just a circular disk, as it is. It doesn't have to be like this, but it cannot sense the entire environment at once. And there is information that is of interest to this robot. For simplicity, let's assume that it is some vector or maybe some scalar eventually that corresponds to each point of this environment. Could be that I care to measure temperature or the wind field or something. So we have still our dynamical system. And now we are going to consider that our environment is just this spatial temporal model. So you have that your m dot is subject to some Gaussian noise, just for the sake of having a toy example here. And you have your sensing model. So your measurements are going to be following, this model here, where I'm going to also assume some measurement noise. And the problem that we were thinking is that, okay, we want the robot to go and explore and maximize the quality of the information collected through that exploration. Which of course is already, a not well-defined problem from the perspective of, well, we have to be more specific about what we mean with quality of information collected. So we kept thinking about that. And of course, that's not a new problem again in the literature from the perspective of you're interested about learning something about this, about your environment, modeled as M. We want essentially, one way of encoding that is the quality of information can be encoded in terms of what is the level of uncertainty that you have about this random variable M. And then the natural way of thinking about it, or one natural way of thinking about it, is in terms of differential entropy. So you can define what is the differential entropy of this random variable M. But then you can see that this entropy is going to take values, from -infinity to infinity. If you want to start making use of it as, a cost functional or a metric, like something that you would like to quantify a little bit more, then it might be less intuitive to have it take all possible values. So we did a rescaling. That was Dev's work, Dev's idea, and he scaled the differential entropy in this form so that we have now a similar measure of information quality that we call clarity. Why? Because now with this scaling, you're going to have something, the output of this function is going to be between 0 and 1. And 0 means that you know nothing about this point of the environment there. Or you can think of it as, infinite covariance at the highest uncertainty. And 1 is I know everything about this point. It would be perfect knowledge in the noise-free setting, okay, in the ideal setting. So then with that, if you now see what is the problem that we want to solve, is that I have a dynamical system over which I want to collect measurements. And I want to collect measurements of this guy here, M. And I'm going to just consider it a scalar for simplicity for now, but that holds also for the M-dimensional case. And you also have a sensing model, the one that I used before. So how you can, and the first thing that we used in order to estimate this M, based on the structure of the system, was a Kalman filter in order to simulate the measurements. And then the estimate then of your M hat, is going to be a Gaussian distribution with mean and covariance that are given out of these expressions here, which, if you notice, not surprisingly, they depend on how you sense, what is the uncertainty about your sensing model, what is the current uncertainty that you have about the environment, and so on. Like, it's a Kalman filter. So, and then another interesting relation that you can notice here is that with the way that we have defined clarity, you can show that for a random variable, for a Gaussian random variable, the clarity is given out of this information for us in the scalar case. And so if you take the clarity dynamics, you have linear, nice closed form expressions, you can write them in this form. And so on one hand, it says that being able to measure, that's your output matrix, increases clarity, not surprising, right? The fact that you have a stochastic environment that keeps evolving decreases clarity, again, not surprising. And in fact, an interesting question, connection that we also made with respect to our earlier work is that this is very, very, very similar to coverage control structures that people have proposed in the literature, where essentially the sensing function and the decay rate are chosen somewhat heuristically. But here, clarity gives you essentially the principled manner of describing what is the rate of change of information and hence confidence for the modeling, of course, that you have chosen. Okay, so then what do you do? What can you do with that? Like, we're thinking, could we start maybe thinking of other interesting problems about how to control for information gain? And a problem that you came to mind was, can we see something if we have a time budget on executing our mission? Because again, constraints and so on, maybe you have a limitation on how much time you have available in order to collect these measurements. And we have like an environment and our dynamical system. Can we say something about how we can acquire a clarity level, a target clarity level, and how to do that? So the connection that we made there was that, well, essentially you have an augmented system that has your vehicle, your state, your system dynamics, and also has your clarity dynamics. And altogether, you can see it again as a reachability problem, if you think about it. So you can define, for example, that this quantity M, this model M, the state that you want to estimate, will be perceivable by your given system to a given clarity level, Q star, that you will have to choose at the time t from an initial condition of initial states and initial clarity level, if there exists a controller such that the closed loop system trajectories are going to be so that at the end of the time horizon, you will have reached your desired clarity level. I'm just formulating essentially a reachability problem over the, if you wish, the actual trajectories and the information trajectories of my problem. And again, inspired by reachability, you can define even the perceivability domain. as the set of initial conditions of states and initial clarity from which you're going to be able to perceive, using that clarity dynamics model, your quantity M to a desired clarity level within a finite horizon time t. And so essentially, we were thinking of it as, putting together reachability and observability and information gathering over the trajectories. And with this formulation of the augmented system, you can have a characterization of how can I reach the desired clarity? So how can I reduce the uncertainty to the extent that I will set, while taking into account the model, the sensing of my agent, of my robot, the dynamics, the constraints of my robot, and so on. So, and in effect, you can, again, it's a reachability problem. You can write down what is going to be the value function of the corresponding optimal control problem. You can do your dynamic programming exercise here, and then you can characterize what is the perceivability domain as a given level set of the value function of this problem. And you're going also to be able to have an optimal controller that will satisfy your objective. Of course, that comes with a cost of, you will have this optimal controller if you are able to compute it for a high-dimensional system. So you are limited by reachability on what type of systems you can address. So just as a toy academic example, we did some computations of perceivable sets for our clarity dynamics, meaning the information gathering with a Kalman filter, and single integrator dynamics for a very simplified model for a boat. Consider this to be a sensing, so this is like an ocean environment. This is a drift along this direction. And this sensing region is where you need to go in order to collect measurements. So we wanted to essentially compute what would be the initial locations of your XY environment, of your states X and Y, X1 and X2, and what would be the corresponding initial clarity levels by solving this optimal control problem, from which, if you apply your optimal controller that you get out of your perceivability computation, you will have a trajectory that will take you with the desired clarity level to the desired sensing region. And if you're interested to see how such a trajectory would look like, that would be, for example, from that initial condition, like you will get a controller that will make you do this loop. Why do you have to do this loop? Because of the drift you have, and because your control input limitations, you have to keep going back and forth, in the loop in order to keep collecting measurements only from the green area. And if you want to see that indeed the dynamics matter, as you were expecting, if we use like a Dubin's boat, so a constrained vehicle dynamics, then the corresponding trajectory that we get is different, not surprising. And also the clarity levels that are attainable are different, because it's more difficult for the Dubin's boat to do this loop there in order to keep collecting the measurements. Okay, and other things that you might find interesting connections with these concepts is that we have identified connections of clarity and perceivability with ergodic coverage controllers. And in order to be able to circumvent the issue with high-dimensional systems, how are those going to be useful computations and useful controllers? Well, you can try to relax them with control barrier functions and be able to encode an approximation of the clarity targeting problem with a control barrier function instead of solving for the optimal control problem. And if you are interested in seeing further work on that area, in this CDC, it was going to be the previous day, we have an extension of these exploration methods to the case that we are really using clarity and corresponding planning controllers in order to learn now a model that is modeled as a Gaussian, as a GP, instead of, you know, the simplified case study that I showed in more detail in the slides. And I talked about adaptation as well. So we have been working on components that involve how you can adapt the parameters of the model and the control barrier functions so that you can adjust to environmental conditions that are changing. So here is just a video of the results of some online adaptation of control barrier functions so that this quadrotor, despite the effect of this wind, learns how to go closer to this obstacle. Despite that, the reference trajectory is way more conservative. So it learns a safer path. Actually, here we do have a violation in the online implementation for technical reasons with online optimization. I'm happy to talk about them offline. But overall, this is ongoing work that shows how you can also start talking about adaptation in these problems. And that is also our take in using also offline learning in order to learn those type of control barrier functions and backup controllers that you need also in your gatekeeper. Okay, I was going fast. Then last couple of slides, I would like to acknowledge some of the work of my other students. They have done work on safety critical control with handling a lot of challenges when it comes to constraints and adversarial environments. We recently published a tutorial paper that summarizes some of their work, and just in terms of only simulations and videos, the work of Joseph Breeden, he recently graduated, has addressed a lot of challenges with input constraints, higher relative degree constraints, and disturbances. And he has implemented those problems, particularly on aerospace problems with constraint attitude control and docking of satellites with tight tolerance constraints and disturbances. So there has been quite also theoretical developments on the theory of control barrier functions that I don't have the time to discuss in a single talk. Also, he has done work on predictive control barrier functions that he applied to a deconfliction on dissimilar orbits. But there are also other applications of that in other type of multi-agent deconfliction. If you're interested in seeing his work on impulsive control barrier functions for impulsive systems, then that is going to be the next day. And in part parallel, in a parallel thread, Mitchell Black, he was working a lot on multi-agent control barrier functions and how you can use control barrier functions in order to deconflict agents, and not just in terms of simulations, but also on experimental implementations in our lab. I would like also to acknowledge the work of my student Kunal, that he has worked a lot on control barrier functions under special temporal constraints. And while James Yusevich, he has worked on control barrier functions and resilience against adversarial attacks. So here in this video, what you see is that there are agents that are trying to fool, like to inject the wrong trajectories. The leader is trying to make the followers follow a trajectory that violates safety. But because the overall network is resilient to these type of attacks, the followers do not get off course, and they can maintain safety. one of our newer students, June, is continuing this line of work, and he is also working with experiments. So in this video, you're seeing that the leaders are those that emit the blue light, and there is one malicious agent that emits the red light, and the purpose for everyone is not to get fooled by red, and eventually all be able to maintain blue light. So essentially, they play resilient consensus. And at the same time, along a control barrier function, they are able to maintain the formation and go through this narrow passage. This is part of our ongoing work on how these concepts are going to be relevant to a multi-agent control architecture. So with some conclusions, I start concluding this talk. I think that, this is an architecture diagram that I drew a couple of years ago, maybe when I was submitting my career proposal, and it's already a couple of years ago. So I think that, by now, maybe we have a little bit of, or at least I have a little bit of better understanding on, how these components work with each other. But there are definitely way more open problems and challenges. Some that are of, my own personal research interests is how to still be able to guarantee compatibility and feasibility of multiple constraints and, under uncertainty. We have some solutions, but of course they work under, again, certain assumptions. What's the right way of learning and exploring the safety critical systems, or what it means that maybe you can be, in some sense, risk aware and start encoding novel notions of safety and resilience in this type of adversarial settings where maybe some constraints will need to be broken, especially for robotic applications. How to do perception-aware planning and control, I think, is an ongoing problem. So with that, I would like, first of all, to thank, my students and my collaborators. They're going to be put on the slide. And I would like also to thank the sponsors that have funded our work, and they have made that possible. So with that, I'm good on time. So I'd like to thank you also for coming here today, and I'm happy to take any questions and your feedback. Thank you very much. And a big thanks to all my students. Like, I was feeling very, 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 very proud of, putting their work in the slides. And there is way more work that I obviously couldn't fit in that slide. So a special thank you to all of them that have enabled all these cool things. Yes.
So whenever I see a new work on control barrier functions, I always have the same question, which is, in a lot of the safety, if you talk about a function that quantifies whether a trajectory is safe, a lot of times that function is going to include both state and control, right? Because
yes.
So for example, if the control force is too large, then your system breaks.
Mm-hmm.
So what can you say about, can you extend control barrier functions to problems where you have combined state and control functions? Are there just fundamental problems with that, or is that?
Yes, so if I understand your question, you're saying that, first of all, there are control input limitations, control input constraints, that in the very first slides, I was not taking them into account because usually these give you the theoretical guarantees.
Well, so let me give you an example. So like in a lot of the systems that I work on, there's a constraint on the power that you actuate with. And that would be the product of control input and some co-located output, which depends on the state. So it's the product of the two.
Okay.
And you need to keep that within some safe set. So the question is, like, if it's something that involves both state and control, or is our CBFs just naturally only applicable to?
Well, yes. So I haven't thought about that particular modeling. It's probably something interesting to explore. My quick answer here is that for this class of problems that you are writing down, you need to be able to write something that constraints is a quadratic program. So you want to be able to write your constraints to be linear with respect to the control input, right? So then if you have some form that may be under some sort of, I don't know, decomposition, small, slow, scale decomposition also, maybe you have a slow varying system, and then you can still have some sort of piecewise structure where you have QPs, 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 QPs. Then in that case, I can see how directly these methodologies can be applicable. If you could extend those further to other classes of systems, I think that would require, more serious studying.
Something that maybe you mentioned, but I missed it, for your ISS observer. Mentioned the bounds that ISS observer gives you can be so conservative that it can be completely useless. So depending on the condition number of the P matrix and the reliable function. How can you use that to make sure that the control is even stable?
So you have some technical assumptions that the initial estimation error is small enough, right? If I remember correctly. So it's a good point. I will have to go and read again the paper, but you have some condition on how bad your initial estimation is going to be, but it's input to state stable, right? So you have you get an even more conservative bound with this M function. That's your exponential, the function that exponentially bounds the response of your observer. And then, but this is input to state stable. So, eventually that you will get better and better. So if you have a very large estimation error, you will have to start even further into the inside of the safe set. So these are coupled with each other.
Disturbance as well. We have a disturbance term as well, right? So
About the disturbance.
yeah, bounded disturbance gets multiplied by something depending on your observer design. So it's not just, if it's bounded doesn't mean that it can be fixed. So it's, even if you do H infinity observer, it will be like signal norm observer, not vector norm observer. So vector norm bounded.
Yeah, I mean, the way I was thinking about it when I first worked on this was eventually you will start to get to small enough errors, even if it's a bounded non-zero error. So what you could do at the beginning is you have to stay sufficiently far inside your safe set, evolve for a little bit of time until your state estimate becomes sufficiently small, state estimate error becomes small. And then you can start to explore the boundaries of your safe set. But you're absolutely right. Depending on the condition numbers and depending on the class K function that acts on the disturbances, you could be very, very conservative. And that's where the second type of observer, the bounded error observer, comes in. So perhaps you could do like two different observers that act at the same time, one which is much lower gain, one which is higher gain, and you can use the intersection of those as your state estimate.
Yes.
Just a clarifying question. When defining your perceivability set, what information or information about the structure of your uncertainty in the environment do you need to know?
That's a very good point. So it's really an open-ended question even for us. What we have defined it for is only for an environment that is subject to Gaussian noise right now. So that is the case studies that we have studied. But eventually, one of the questions that we would like to keep studying is what it means if you have some other type of uncertainty, and what it means what is the right estimation or learning law that would be more appropriate for that environment. So. Yes.
Quick question, is that clarity always a scalar, or can it be, can you always extract everything into a scalar?
I think that we are extracting everything into a scalar right now, but it can be of a dimensional, n-dimensional vector, right?
So for an n-dimensional vector, we define essentially the determinant of the covariance matrix that defines the clarity. In the ergodic control stuff where we're doing coverage, we have clarity for each point in the state space that we care about.
And the dynamics are still as simple, that you do the determinant?
Yes, so especially the CDC paper, that's where we had some amount of interaction between different points in state space. So that means that it was a process measurement. So we said making a measurement here influences our information somewhere else, and we can characterize how much that information is.
Okay, so now because we're 4:30, let's take the rest of the questions. I also have questions.
Yes.
Offline, and let's take the speaker.
Thank you.
Next.
Actually, is it too much today? Guys, all the kudos go to Dev. It's his work. That's his PhD defense. So
You're gonna have to do more for your plenary.
I told you. So, but yeah, yes, I think that maybe for CDC I can maybe tune down some of the robotics type of arguments and make it more technical. I don't know.
That was very good at that. Well, it was funny technical. Yeah.
We were to use it actually, I thought the reason it was asking in the practice.
Yeah.
Stuff. If you were working on, issues.
Okay, good. It's something that I also try to get them to continue working.
So we want to learn.
Like it?
Yeah, I think the technical level was great.
Okay, okay.
Later parts, it felt a bit advanced, but.
The little parts I have, I don't know if you noticed some of them. The papers. Yeah, these are
Yeah.
But you can fix them easily.
Yeah, yeah.
So I think.
And that would be the only thing is, I totally agree that the technical depth is perfect. There's a lot when you're talking
Yeah.
very fast. So it would only be, is there anything that you would want to give yourself
I
a
would-
little bit of
Yeah.
time to